Okay, chapter 6 is properties of the normal distribution. And I want you to remember that when we did binomial on the calculator. We will be able to find probabilities for the normal distribution using the calculator just like we did for the binomial. But what I want you to remember is that in the binomial you had to be careful and watch where the probability was that you were looking for. Was it more than some number, then you had to use 1 minus. If it was less than some number, then you used CDF. And if you wanted an exact value, you use binomial PDF. In the normal probability, you won't have to decide between PDF and CDF. Because in normal probability, you cannot find the probability that X takes on one single value. That doesn't work. Not in normal. You can find the probability that X is more than something or less than something very easily. And we'll use the calculator to do that. We won't use paper tables to do that because there's no point learning how to do both. But before you learn how to do that, you need to understand what the normal curve looks like. Binomial probability curves look different depending on the sample size, the value of P, and things like that. So sometimes binomial curves look normal and sometimes they're skewed. It just depends on the sample size and the probability itself. But in normal, it always looks this way. It is always a bell-shaped curve. The properties of the normal distribution, there are 3. Actually, there's 3, but then there's 3 more that go with a particular rule. The first rule is that the curve is bell-shaped. It looks like an upside-down bell. And its highest point is over the mean, which is mu. Okay? So the center value on your notes should say mu. The center value in that curve should say mu. The second property is that the curve is symmetrical about a vertical line through the mean, which means that if you took your notes and you took that picture of the normal curve that you have and you were to fold that curve exactly in half down through the middle, that middle line would go through. If you were to draw a dotted line right down the middle, it would go through the mean. And what that means is that the left half of the curve and the right half of the curve look exactly alike, except that they're mirror images of each other. That's what it means to be symmetrical about the vertical line through mu. There's a lot of things that are symmetrical. Circles are symmetrical. You can fold them in half, and the right half looks just like the left half. Squares are symmetrical. You can fold them corner to corner, and the right half looks like the left half. It's 2 triangles. Or you can fold them in half vertically. You can fold rectangles in half vertically or horizontally, and the top half and bottom half match, or the right half and the left half match. Ovals are symmetrical because that's just a stretched circle. Some triangles are symmetrical because you can fold them in half and the right half looks like the left. But if you've got one that's kind of lopsided, it's a triangle that's long on one side and short on the other, if you fold it in half, it's not symmetrical because its 2 halves don't look alike. So that's what symmetry means, is if you fold it in half along what's called an axis of symmetry, that the right and the left half will look just alike and have the same properties. And that's going to be important. The third property that's important to you is that the curve never approaches the horizontal axis, It approaches the horizontal axis, but it never touches it, and it never crosses it. It just gets closer and closer and closer to it. Okay? But there are no x-intercepts. If you remember that term from algebra, there are no x-intercepts. There is no place where the value of the normal probability is actually 0. Even though you would think there would be, there actually is no place you can say that the probability is 0. You may have something that's approximately 0 because it is so small, but it never actually is 0 because it never touches the axis. Now, the two things that aren't mentioned on the slides as properties are those 2 points right there that are exactly 1 standard deviation to either side of the mean, and those are called inflection points. If you were going on to a calculus-based statistics, I would emphasize those to you because an inflection point is where the curve starts going down quite as fast and starts to slow down and flatten out. So it's actually those inflection points that cause it never to cross. They just let it keep going slower and slower and flatter and flatter. The empirical rule only works on symmetrical bell-shaped distributions, which is normal curves. And notice that bell-shaped is blue because it applies to the bell-shaped distributions. It works on symmetrical distributions, but the problem with it is that there's not just one symmetrical distribution. There is another symmetrical distribution called the uniform distribution, where everything is approximately the same height. In other words, it looks like a horizontal line. Don't confuse that with bell-shaped. The empirical rule only works on bell-shaped distributions. So at this point, and I skipped over something right now, and I'm going to come back to it. At this point, we're going to talk about the empirical rule. The empirical rule says that approximately 68% of the data values lie within 1 standard deviation of the mean. So the area from the mean minus 1 standard deviation, which is right here, to the mean plus 1 standard deviation, which is right here, contains 68% of the probabilities, or 68% of the data values. And since that's symmetrical, that 68% is cut in half into 34% to the left of the mean down 1 standard deviation, and 34% to the right of the mean up to plus 1 standard deviation. So if you were to select a random value x that had a normal distribution, and you were to figure out that it was within 1 standard deviation of the mean because you took the mean and added 1 standard deviation, let's say the mean was 10 and the standard deviation was 5, and you added 10 plus 5 and got 15, if your random selection was 12, that means it's within that 68% that's in that middle chunk. Okay? Same thing on the other side. 10 minus 5 would be 5. So if you got a 9, that would be a relatively high probability that that would happen. Because 68% of the time you should get a value between 10 minus 5 and 10 plus 5. Okay? The next rule should look a little familiar to you because it actually is the basis for the range rule of thumb. The range rule of thumb says 95% of your data will lie between the interval, the mean minus 2 standard deviations up to the mean plus 2 standard deviations. So going back to my mean of 10 and a standard deviation of 5, 10 minus 2 times 5 would be 0. and 10 plus 2 times 5 would be 20. So if that was indeed the case that we had with this normal curve, then between 0 and 20, I should have 95% of the values of x. And anything that lies outside 0 to 20 would be odd or unusual because those happen less than 5% of the time. So approximately 95% of the data values lie within 2 standard deviations. That's this green area plus the big chunk of blue area plus the little piece of green area. And again, this little piece of green has the same percentage as that little piece of green because of symmetry. Okay? And then the last one says that almost all, approximately 99.7%, which is almost all, of the data will be within 3 standard deviations of the mean. So in using the mean is 10, the standard deviation is 5, then 10 minus 15 would be negative 5, 10 plus 15 would be 25. 99.7% of all my data values should lie between negative 5 and 25. Okay? So here's an empirical rule example. The life of a particular type of light bulb is normally distributed with a mean of 1,100 hours and a standard deviation of 1,000 hours. I'm sorry, 1,100 and 100 hours. Okay, so here's my mean, this is mu, and here's my standard deviation. That's sigma, and it's going to be 100, and it's mu and sigma because it's a probability distribution, so it's a population. And our question is then, what is the probability that a light bulb of this type will last between 1,000 and 1,200 hours? So in order to answer that, remembering the normal curve, when it tells me that there's a mean of 1,100 hours, that means that center value is 1,100. Okay? And when it tells me the standard deviation is 100 hours, that means that mark below is 1,000 hours because this distance right here is 100. And the same thing on this side. So from the mean up 1 standard deviation would be 1,200 hours. So that center value is mu, and then this is mu minus 1 standard deviation, and this is mu plus 1 standard deviation. Now if I go down 1 more standard deviation, go up one more standard deviation, then this is going to be 1100 minus 2 times 100 is 200. Because that distance is also 100. And 1100 minus 200 is 900. And since this is also 100, 1200 minus, or excuse me, 1100 plus 100 is 1300. And then when I get to 3, then this is going to be another 100. So 1100 minus 100, 200, 300 is going to be 800. And the same thing on this end. 1100 plus 100, 200, 300 is 1400. So that's the curve that we're talking about. Okay? That's the actual curve that we're talking about. And notice here that I did not make this cross. What's going to happen here is it gets just really, really flat, but it continues on forever. So then our question says, what's the probability that a light bulb of this type will last between 1,000 and 1,200 hours? Here's 1,000. Here's 1,200. And my empirical rule tells me that this is within the interval mu minus 100 or mu minus sigma to mu plus 100, which is mu plus one value of sigma, and that's 68%. Okay? The curve represents probability. And one thing to remember that I haven't mentioned, but remember you have two things about probability you always know to be true. All probabilities are between zero and 1, and the sum of all the probabilities is equal to 1, which tells you that the area under the curve equals 1 or 100%. Okay? Okay.
Could you go through that new stuff again? I don't want to get why.
Because this is the properties of your curve. Properties of the curve says the mean is at the middle. It says each one of these little marks is one standard deviation, which is 100. And your empirical rule says that the mean minus one standard deviation, which is where this is, to the mean plus one standard deviation, which is what this is, that between those two you have 68% of your data. This is just a summary of all of the last several things that we said. It's just an illustration of it.
How do we get 68%?
Because that's the empirical rule. Pull this back up here. The empirical rule says, since this is the mean, and this is the mean minus one standard deviation, and this is the mean plus one standard deviation, it says the probability that an X will be between those two blue lines is 68%. Okay? That's within one standard deviation of the mean.
So it'll always be 68 if it's in between the first, like, it'll always be those same numbers?
Yes.
Okay.
And then the same thing, if it's the mean minus 2 standard deviations to the mean plus 2 standard deviations. Within 2 standard deviations, you have approximately 95%. Okay? And then if you go all the way out to 3, which is within 3 standard deviations, notice that the curve kept going after that. But it was really down very, very, very close to the x-axis. So there's not much area left between the curve and the x-axis. So even though it's not 100%, it's really close to 100% by that point, which would tell you that it's virtually impossible, if it's a symmetrical bell-shaped distribution, to have an x value that's either more than 3 standard deviations above the mean, or less than 3 standard deviations below the mean. I want to be careful and say that right. Okay? That's what I'm going to say is, only about 0.3%, 0.3%. So values that high would be very unlikely. Values below here would be very unlikely. Or very unusual. Okay? It would be unusual, actually, if they were outside these two. It would be suspicious. Not impossible, but very suspicious. But if it actually lies outside this boundary, that would be nearly impossible. So these would be unusual. But these would be way more than just unusual. They would be virtually impossible. Okay? So now we're getting into degrees of unusual. Before I talk about the standard normal, which is next in your notes, I'm not sure. This is a little earlier in your notes, but there's not a PowerPoint slide for it. So I wanted to talk to you about this right now. Remember from chapter 3, this is important, that the standard deviation is a statistic that tells you how tightly all the various examples are clustered around the mean. When examples are tightly bunched together, and the curve, the bell-shaped curve, is steep, then the standard deviation is small. That would be like this. When the values are not tightly together, they are spread apart, and the bell-shaped curve is relatively flat, like this one. Then the standard deviation is large. Less variability, small standard deviation. More variability, large standard deviation. Okay? Both of these curves are centered over the mean, which is mu, which is 0 in this particular case. But notice here, the standard deviation amounts are very, very small. Maybe like 1/2. Whereas if I'm looking at the green curve, the standard deviation amount would be rather large, maybe about 2. Okay? Same mean in both cases, different standard deviations. The one that we're going to talk about next is the one that's kind of like in between those two. And that's where the mean is equal to 0, and the standard deviation is 1, 2, 3, 1, 2, 3. So sigma would be 1 in that case, with that blue one, the one in the middle. Okay? But again, wide, flat curve, large standard deviation. Skinny, steep, narrow curve, small standard deviation. Others are in between. And one of the ones that's in between is called the standard normal curve. The standard normal curve has a mean of 0. And it has a standard deviation of 1. All of those little increments there are 1. Okay? And of course the total area under the curve we know is 1 because that's probability. And the sum of all the probabilities should be 1 or 100%. That's from chapter 4. What I want you to understand, the very important thing here to know, is that the z-score tells you the number of standard deviations between the original measurement, which is an X measurement, or a raw score, and the mean of the original measurements. We're going to learn how to convert between a normal distribution and a standard normal distribution, which is what this one is. Once we understand how to calculate the area under the curve. One of the things that's absolutely imperative that you remember is that for a normal distribution that is a standard normal, that word standard is very important because it's a way of standardizing things. The standard normal distribution always has a mean of 0 and it always has a standard deviation of 1. Always. That's always going to be the case. So you need to remember that. Now I'm going to warn you, in my stat lab there are going to be some cases where they're going to tell you using the calculator command that you can leave out certain information, and I'm going to tell you no, you can't. If you're doing it for me, you're going to put that information in. And they're also going to tell you that for infinity and negative infinity, that you can use certain very large or very negative numbers. And I'm going to tell you, no, you can't. You have to use this. And I'll explain why when I get there. But for those of you that may be working ahead in my math lab to learn how to do this, just be aware that when I use the calculator commands, I'm a lot pickier than the person that wrote all that stuff for my math lab. Okay? And since this is my class, we're going to do it my way. I've been at this longer than the person that wrote the lesson. In fact, I used to work professionally as a statistician, so that's why there's some things I'm pickier about than they are. So let's go back to the PowerPoint for a minute. You're going to need your calculator. And we're going to learn how to calculate what's called a standard score. The z-value, or z-score, that tells the number of standard deviations between the original measurement and the mean is called a standard score. The z-value is in what is called standard units. Okay? It's called standard units. When we do these are just things to be aware of. When we calculate these on the calculator, we're going to round our z-values to hundredths, not thousands, not whole numbers, not tenths. It has to be to the hundredth place. We're going to leave area results, which is your probabilities, with 4 digits to the right of the decimal point. So we're going to round to 4 decimal places. And now we're going to go to the examples in the notes. So to calculate an area under a normal curve, we're going to use the command on your calculator called normal CDF. And that's to calculate area. You need to associate calculating area or probability with normal CDF. You access this using second bars. I'm going to see if there's a way I can make this image a little bigger, because I know that print's kind of small even though you do have. So what this is going to require you to do, and this is also important, normal CDF requires you to enter a left boundary and it's going to require you to enter a right boundary. So you're going to have to tell it where to start and where to stop. And that's going to be separated by a comma. The boundaries that you use are going to depend on the problem that you're working with. Keep in mind, it's very important to draw a picture of the area that you're trying to find before you use your calculator. Do not memorize some way to enter it into your calculator so that you can skip drawing the picture. Because what happens when you do that is that you do it wrong. Because there is no process to memorize. If you've got the picture tells you what you need to do. So you have to draw the picture. Don't skip that step. I'm not going to let you skip that step. Even if you get the answer right, you skip that step, you're not going to get full credit. That's how important it is that you draw that picture. So we're going to practice with some examples. Here's our first example. I'm going to make this as big as I can so that we can see just what we're looking at. Find the probability that Z is less than 1.27. First thing that you need to do is take into account that this is a normal curve. And if it's a normal curve, that means the mean is 0 and the standard deviation is 1. So that's 0, 1, 2, 3, 0, negative 1, negative 2, negative 3. Where is, on that line that I just numbered in, where is the number 1.27? Is it here?
No.
Is it here? Is it here?
No.
How about here?
No.
How about there?
Yes.
Okay, because it's a little bit more than 1, right? So 1.27, this would be like 1.5. That'd be about like 1 1/4. So 1.27 should be right about there. So that should be the first thing that you do, is you label in where that Z value is. Then you go back and you look at your sign. Am I looking to the left or to the right? Looking for the area to the left. So when I get this answer, should my answer be closer to 1 or closer to 0? Closer to 1, because that's a big area, right? Okay, the way the normal CDF command works is you want the lower value, then you want the higher value, then you want the mean, and then you want the standard deviation. That's always what you want. And you have to have all 4. I don't care what the examples in my math lab say, you have 4. Not 2, 4. These are always part of it. So with that in mind, before we ever try the calculator, we're going to put normal CDF. The low value in this case, remember you have to go down to negative infinity because that curve goes on forever. It never stops. It does not stop at negative 10,000 like the instructions in my math lab says. In fact, if the mean was 10,000, that might be a problem. Okay? You can't actually put a number on it. So what we want to do is we want to make sure we go to negative infinity, or at least as close to negative infinity as we can. Now, without making a contest out of it, I have in the past, I've had people actually look for the infinity button on their calculator. I will tell you that if you hit your second and your 0 button, that list contains every single symbol and every single command your calculator knows. So if we hit the down arrow key, if there's an infinity symbol on here, we should see it. By the way, that I right here, that's the imaginary number I. That is not infinity. Surprising how much your calculator does know how to do, isn't it? Okay, now we're finally getting to symbols. And you know right here, this is what infinity looks like, okay? Anybody see one? It's because there's not one. Okay. Review of scientific notation. What's that? What number is that?
Is it 10 million?
Well, basically, it's a 1 followed by 10 zeros. One, two, three, four, 5, 6, 7, 8, 9, 10. So there's thousands, millions, billions. So you're close, 10 billion. Okay? Pretty big number, huh? They don't measure the national debt in billions. They measure it in trillions. That's a trillion. 18 zeros. Okay? What would that represent?
A really large number.
A really, 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 really large number. Even in Star Trek or Star Wars dimensions, any kind of scientific or sci-fi dimensions, that's a huge number. We can't even imagine a number that huge. All I can do is tell you that's a 1 followed by 99 zeros. Now we could always go one more and say it's 1 followed by 100 zeros, or we can go even higher than that, say 1 followed by 1,000 zeros. But can you imagine anything that's bigger than that? Anything that you could actually picture in your mind that's bigger than that amount? Because I can't. I cannot envision anything that's bigger than that amount. What if I put a negative sign in front of each of these? What's the difference in the exponent being positive and negative?
The least amount you can imagine.
That becomes the least amount you can imagine, because, for example, this would be that, which is pretty small. But this would be a decimal followed by 98 zeros before you get to a 1. And I can't imagine anything that small either. So here's the situation. This is what we're going to do. We're not going to use negative 10,000 for infinity. That's nowhere near infinity. We're going to use negative 1 times 10 to the 99th power. But it's more easily written on your calculator as negative 1 e 99.
Can you scoot over just?
Yeah, I'm trying to make it move right now.
Thank you.
So for negative infinity, we're going to use negative 1e 99. So when we enter in this command, get the rest of these out of the way because we're not going to get to them today anyway. When we enter in this command, normal CDF, we're going to use negative 1 e 99 for our lowest number. That's negative infinity. We're going to enter in z equals 1.27 is our upper number. The mean of a normal distribution is 0. And the standard deviation of a normal distribution is 1. That's the command that we're going to use. So now let's put it in the calculator and see what we come up with. I'm going to turn the calculator on. You will never, 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 never use item number 1 on this distribution, on this menu. Forget that it exists. We will never use normal PDF. What normal PDF actually tells you will be the length of that line right there, which doesn't tell us a blessed thing. No help whatsoever. So we're going to go and use number 2, which is normal CDF. And then we're going to enter in the numbers in this blank. -1, and the exponential E is second comma. It's above your comma key. Then we're going to put in the 99. Then we're going to put in the 1.27, because that's our upper boundary. Then we're going to put in the 0.
Well, we put commas in between all of
You
them.
put in commas in between all of them. And then we're going to put in a 1, and since the 1 is the last value we need, we're going to close the parentheses. Has everybody got your calculator screen looking like that? Okay, then we're going to hit enter. And the answer that we get says that this area is 0.89795, which rounds then to 0.8980. So remember, you need to go on and look at the 5th decimal place to decide how to round. And since when you round the 9 up, it becomes 10, then that means that 7 also rounds up and becomes 8. Okay? You understand that process? Okay, let's try one more example. We'll get the calculator out of the way. Same situation, since this says Z. 0, -1, -2, -3, +1, +2, +3. Do you have a question?
Yeah, I did, about the area. So what we got there, is that the area? Or
Yes, that is the area, which is the probability. Okay? And in this case, then our answer to our question is the probability that Z is less than 1.27 is 0.8980. Okay? I'm sorry, I didn't think about that. I hadn't made that clear to you. So let's try the second example. Because this is Z, then we label in the axis with Z values. And because it's Z values, the mean is 0, the standard deviation is 1. Then the next thing that we do is we look and see where is the number -2.71. Which side of 0 is it on?
The left.
How do you know it's to the left?
It's a negative.
Because it's negative. Very good. Okay, is it between here and here or here and here?
It's between 2 and 3.
Okay, between 2 and 3 because it's less than -2. And because it's less than -2 and that's more than halfway, then we'll make it a little closer to -3. So that's where it's equal to Z. Now our sign up here says it's to the left of that, right?
Yeah.
So we're looking not for all of this up here. We're looking for this little bitty bit right here. Okay?
How can we tell if we're supposed to look to the left side or like the small shaded portion or the larger shaded?
Because the arrow in the Z points to the left. So if the arrow points to the left, it's to the left of the line. If the arrow points to the right, it's to the right of the line. Okay? And then once you've got your picture drawn, once again, what's your lower boundary? What's the first boundary? Negative infinity, which for us is -1E99. So our command,
We'll always use the 1E99.
yes, either positive or negative, depending on which end.
Okay.
If it was on this end, then it would be +1 E99 for the really big number. So the way we're going to get this is normal CDF. The low number is -1 E99. The upper number is -2.71. The mean of a standard normal curve is 0, and the standard deviation is 1. So that's what we're going to put in the calculator. Okay? So you put that in your calculator and you tell me what you get. Did you get a very, very large probability or a very, very small probability?
Very small.
Very small. I got .00336. So what does that round to? Okay. And that's a very, very small probability. Okay? Very, very tiny area. Very small probability. So what your picture shows you should be backed up by what your calculator tells you. And if it doesn't, you missed something somewhere. Okay? So be sure to go back and figure out what you were doing wrong. Yes?
Why isn't it .0035?
Because it's .0036 and the 6 is more than 5, so it says round the 3 in front of it up to 4. Okay?
Oh, okay.
Go back and review your rounding rules. So we're gonna do one more, and then I'm gonna take questions in case anybody has any. We're gonna do example 3. There again, normal curve, 0, 1, 2, 3, -1, -2, -3. This one has 2 boundaries. First boundary is 0. That one's easy to find. Second boundary, 1.24. That's between 1 and 2, closer to 1. Where does it say Z is? It says it's between. Okay? So we're looking for an area that's less than half. We know it's less than half because half of it is over here and half of it is over here, and it's not all of this half, it's part of it. And it's probably more than 25% because it looks like it's a little bigger than the part that we didn't color in. But that gives us a ballpark idea of what it should be. So our command normal CDF, 0 is where we start. 1.24 is where we stop. The mean is 0 and the standard deviation is 1. So see what you get. What'd you get?
0.3925.
Okay, 0.3925, because the number actually is 0.3925. I believe the next digit's a 1. So we just leave it off. And that is the area that we shaded in yellow. So that's our probability.
So will we ever have to use the positive infinity, or will the number always be just?
No, we will use positive infinity as well.
So sometimes we'll get the low but not the high.
Yes, if it doesn't give you the high is positive infinity. Okay, so we will pick up an example 4. I will change the due date for assignment 1 because you're not quite ready to finish assignment 1, so I'll move it ahead to Friday. I wasn't sure how far we get today, so I will change that. Do your homework on chapter 6. Be sure and check for that, check for the extra assignment that I was going to put up before I see you next time. Just check those. When I post it, I'll send out a reminder.
Yeah, that's what I was thinking.
I'll just let it fly now.
See, I guess